In this video, we'll talk about dealing with definite integrals with the substitution method. So all of our previous work with the substitution method used indefinite integrals. What happens if we have a definite integral instead? Well, the main issue is we have to deal with the bounds on this integral. And the point is this. We had something like the integral from a to b, f of u of x times u prime of x dx. We use g's instead of u's, but the idea is still the same. And we know this equals an integral of f of u du if they were indefinite integrals. But now this is a definite integral, what happens? Well, the fact that these are a and b here are really telling us bounds on x. This is really a bound at x equals a and a bound at x equals b. So I need to convert those over here to get some sort of u bound. How do I get that? Well, I know that u is just u of x. If I want to find the lower bound, I can just plug in u at the point a, because a was the x value that corresponded over here. And at the top, I can plug in u of b. So this is really here what this method now tells us, is that if I want to do a definite integral by substitution, I have to change my bounds, and this is how I change my bounds. I change my bounds by plugging in for the bounds the function u evaluated at each bound. Without all the colors, it says the following. Integral from a to b, f of u of x, u prime of x, dx equals the integral from u of a up to u of b, f of u du, which I can now solve directly. For our previous problems, you had to do the substitution, do the integral, and then go back to x. But now, this here is a number. I can just solve for this number and be done with the problem. So this here gives rise to two methods for solving these sorts of problems. Method one is change the bounds and then just solve the new problem in terms of u. Or method two, remove the bounds entirely, solve the indefinite integral problem, convert back to x, and then plug in your x bounds. And we'll see how both of these work with examples on the next pages. We compute the integral from 1 to 4 of x times x squared plus 1 cubed dx. So from doing indefinite integrals, I know what I should do here, and I should set u to be x squared plus 1. So du is 2x dx, or 1/2 du equals x dx, which I have in my problem. So what does this become? The integral from 1 to 4 of x squared plus 1 cubed dx becomes an integral 1/2 u cubed du, but what are my bounds? My bounds are from u of 1 to u of 4. U of 1 is 1 squared plus 1 is 2. U of 4 is 4 squared plus 1 is 17. I can then integrate this and solve the problem directly. I get a 1/2 times a 1/4 u to the 4th from 2 to 17. Using my thermal calculus there. So I get a 1/8 17 to the 4th minus 2 to the 4th. What about the other method? The other method says, forget the bounds, solve the indefinite problem, and then plug in the limits from there. To do that, I would just ignore the limits, do my same substitution to get 1/2 integral of u to the 3rd du, integrate to a 1/2 times 1/4, or a 1/8 u to the 4th, plus c, and then convert back to x using the fact that u is x squared plus 1. So I would get 1/8 x squared plus 1 to the 4th plus c. Now I can plug in my x bounds of 1 and 4 and see what I get. And so then I would get that the integral from 1 to 4 of x squared plus 1 cubed dx is 1/8 times 4 squared plus 1 to the 4th minus 1/8 times 1 squared plus 1 to the 4th, which is exactly the same value I got up here. It doesn't matter which way you do it, you get the same answer either way. The one thing you cannot do is write something like integral 1 to 4 x squared plus 1 cubed dx equals 1/2 integral from 1 to 4 u cubed du. That is wrong because these bounds are not u bounds. Those are your x bounds you carried over, and you can't write them there. So something like this is incorrect because now you've told me that your integral goes from 1 to 4 in u, which it doesn't do. It goes from 1 to 4 in x, which is 1 to 17 in u, and is a very different problem to solve. So make sure you either change the bounds when you move the integral or get rid of the bounds entirely and solve it as an indefinite problem. As an example, we're going to compute the integral from 0 to pi over 4 of secant squared x times tan x dx. And we'll do this two different ways. So first method, we're going to set u to be tangent of x, which means du is secant squared of x dx, which I see in my problem. Then this integral becomes what? It becomes the integral of u du from what bounds? Well, tangent of 0 is 0, tangent of pi over 4 is 1. So I get u squared over 2 from 0 to 1, or 1/2. Now method 2 here I can use. I can set u to be secant of x. Then du is secant of x tangent of x dx, which I also see now in my problem, because secant squared is secant times secant. So see the same thing over there. What do I get for this? Well, my integral then becomes what? Well, it becomes integral of u du again, but what are my bounds? Well, secant of 0 is 1 over cosine of 0 is 1, and secant of pi over 4 is 1 over root 2 over 2, which is root 2. So I then get u squared over 2 from 1 to root 2, which comes out to be 2 over 2 minus 1 over 2, or also 1/2. So the point of this example here is the fact that it doesn't matter how you set the substitution. As long as you do one that's correct and work towards the right answer, you'll still get the same answer no matter what you do. That's how all this stuff works. If you do the math correctly from an initial substitution, you'll get to a right answer, and you'll get to the same right answer no matter how you get there. That's the idea of what happens with a definite integral when we want to do substitution. The main issue is you have to also change the bounds and make sure that they match up with the variable you're using before you go forward with the problem, or you scrap the bounds entirely, solve the indefinite problem, and then go back to use your bounds at the very end.